The determinant of a 10 by 10 matrix is a sum of over 3 million terms. 10 factorial equals 3,628,800. But every single one of those terms and every plus or minus sign in front of it is forced into existence by just 3 rules. No guesswork, no arbitrary choices, pure logical consequence. Let's start with 2 by 2 and watch the formula build itself. 3 properties pin down the determinant completely. Property 1, the determinant of the identity matrix equals 1. Property 2, exchanging any 2 rows flips the sign of the determinant. Property 3, the determinant is linear in each row separately. What does that mean? If one row is a sum of 2 vectors, the determinant splits into 2 separate determinants, one for each part. And if a row has a scalar factor, that factor pulls out in front. And these 3 rules are our only ingredients. Everything else about determinants is a consequence of just these 3 properties. Take a generic 2 by 2 matrix with entries AB in row 1 and CD in row 2. Using linearity in row 1, we can split the row vector AB equals A0 plus 0B, so the determinant splits into 2 pieces, one matrix with row 1 as A0 and one with row 1 as 0B. Both keep row 2 as CD. Now split each of these by linearity in row 2. The first determinant becomes 2 matrices, one with rows A0 and C0 plus one with rows A0 and 0D. The second determinant becomes 1 with rows 0B and C0 plus 1 with rows 0B and 0D. That gives us 4 matrices total. Now the matrix A0, C0 has its entire second column all zeros, so its determinant is 0. The matrix 0, B0, D has its entire first column all zeros, so its determinant is also 0. Both of these die. 2 matrices survive. The diagonal matrix with A0 on top and 0, D on the bottom, has determinant A times D. This follows from factoring A out of row 1 and the D out of row 2, leaving the identity matrix whose determinant is 1. The anti-diagonal matrix 0, B on top and the C, 0 on the bottom, needs one row exchange to become diagonal. That exchange flips the sign, giving determinant negative BC. Combining the 2 surviving terms, the final result is determinant equals AD minus BC. 2 by 2 gave us 2 surviving terms out of 4 candidates. Now let's try 3 by 3. Splitting 3 rows with 3 entries each produces 3 cubed, which is 27 candidate terms. Each candidate picks 1 column from each row. Any candidate that picks the same column twice leaves some other column entirely empty. All zeros, a 0 column means the determinant is 0. That term dies. Survivors must use each column exactly once. That's a permutation, like a reordering of the list 1, 2, 3, assigning each row to a distinct column. There are 3 factorial, which equals 6 permutations. Here are all 6, along with their signs, determined by counting the number of pairwise exchanges needed to sort each permutation back to identity order. Columns 1, 2, 3, 0 exchanges, sign plus. Columns 1, 3, 2, 1 exchange, sign minus. Columns 2, 1, 3, 1 exchange, sign minus. Columns 2, 3, 1, 2 exchanges, sign plus. Columns 3, 1, 2, 2 exchanges, sign plus. Columns 3, 2, 1, 1 exchange, sign minus. 6 permutations, 6 terms, each with a forced sign. The pattern is unmistakable. This pattern extends to any n by n matrix. Here is the big formula. The determinant of A equals the sum over all permutations sigma of -1 to the number of inversions of sigma times A1 sigma of 1 times A2 sigma of 2, and so on through an sigma of n. Let's break this down piece by piece. The sigma under the summation sign means we are summing over all n factorial permutations of the columns. The factor -1 raised to the number of inversions determines the sign of each term. If the permutation requires an even number of exchanges, the sign is positive. If it requires an odd number, the sign is negative. And the product chain, a 1 sigma of 1 times a 2 sigma of 2, and so on, means we pick exactly one entry from each row and one entry from each column. Now, how many terms does this sum have? Exactly n factorial, one for each permutation, and n factorial grows incredibly fast. 2 factorial is just 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, and the 10 factorial is already 3,628,800. So even for a modest 10 by 10 matrix, the determinant formula involves over 3.5 million terms. Let's check this formula against property 1, that the determinant of the identity matrix equals 1. Consider applying the Leibniz formula to the identity matrix. In the identity matrix, every diagonal entry is 1, and every off-diagonal entry is 0. Now, in the Leibniz formula, each permutation sigma selects one entry from each row. If any permutation picks an off-diagonal position, that entry is 0, which kills the entire product for that term. So the only permutation that gives a non-zero product is the identity permutation, selecting columns 1, 2, 3 through n in order, which picks out all the diagonal entries, and those are all ones. For example, in a 4x4 identity matrix, a non-identity permutation like sigma of 1 equals 2, sigma of 2 equals 1, sigma of 3 equals 3, sigma of 4 equals 4, would select the entry at row 1, column 2, which is 0. That 0 makes the entire product 0. The identity permutation, on the other hand, has 0 inversions, so the sign is positive 1. The product is 1 times 1 times 1 times 1, which equals 1. Multiplied by the sign of positive 1, we get 1. Out of all n factorial permutations, only this single term survives. Therefore, the determinant of the identity matrix equals 1. Property 1 is confirmed. Here's a common trap. Let's look at the 3x3 anti-identity matrix, which has ones only on the anti-diagonal, that is, at positions 1, 3, 2, 2, and 3, 1. Since all other entries are 0, the only surviving permutation in the Leibniz formula is 3, 2, 1. To find the sign, we sort it back to 1, 2, 3, swap positions 1 and 3, 3, 2, 1 becomes 1, 2, 3. That's just one exchange, which is odd, so the determinant equals -1. Now consider the 4x4 anti-identity matrix with ones on its anti-diagonal at positions 1, 4, 2, 3, 3, 2, and 4, 1. The surviving permutation is 4, 3, 2, 1. First, swap positions 1 and 4. 4, 3, 2, 1 becomes 1, 3, 2, 4. Then swap positions 2 and 3. 1, 3, 2, 4 becomes 1, 2, 3, 4. That's 2 exchanges, which is even, so the determinant equals +1. Notice the 3x3 case gives -1, while the 4x4 case gives +1. For the general n by n anti-identity matrix, the number of exchanges needed is the floor of n over 2, and the sign of the determinant is -1 raised to that power. The lesson here, always count the exchanges, never assume the pattern from small cases. Zeros become powerful in practice. Consider this 4x4 matrix. Row 1 is 1, 1, 0, 0. Row 2 is 0, 1, 1, 0. Row 3 is 0, 0, 1, 1. Row 4 is 1, 0, 0, 1. Out of 24 possible permutations, most hit a 0 entry and vanish. Only 2 paths survive. Path 1 picks columns 1, 2, 3, 4. The identity permutation, its sign is positive, and the product is 1 times 1 times 1 times 1, which equals 1. Path 2 picks columns 2, 3, 4, 1. This is a 4 cycle, which needs 3 exchanges, so its sign is negative. The product is again all ones, giving -1. The total is +1 minus 1, which equals 0. The determinant is 0. Right? We can confirm this independently. Take row 1 minus row 2 plus row 3 minus row 4. Column by column, in column 1, 1 minus 0 plus 0 minus 1 equals 0. In column 2, 1 minus 1 plus 0 minus 0 equals 0. In column 3, 0 minus 1 plus 1 minus 0 equals 0. In column 4, 0 minus 0 plus 1 minus 1 equals 0. The result is the 0 vector. The rows are linearly dependent, which guarantees the determinant is 0. The big formula is not how you compute determinants in practice. Cofactor expansion and row reduction are far more efficient. The formula's true value is conceptual. It reveals that the determinant is a polynomial in the matrix entries with exactly n factorial terms. Each term is a product of n entries, one from every row, one from every column, indexed by a permutation. The sign of each term comes from the exchange parity of that permutation. This formula is the foundation for proving that the determinant of A times B equals the determinant of A times the determinant of B. It is also the basis for deriving cofactor expansion and for establishing Cramer's rule. But here is the key insight. Every term and every sign in the big formula was already determined by just 3 properties. Property 1, the determinant of the identity is 1. Property 2, row swaps flip the sign. Property 3, the determinant is linear in each row. The big formula didn't come from nowhere. It was the only possible answer.